and welcome to our special on the 2021 Shaw Prize. Magnetars were only theoretical objects until two scientists confirmed their existence. Now magnetars tell us much about fundamental physics and have helped prove a number of theories, some proposed by Albert Einstein. Krista Kuvelyato and Victoria Caspi are the co-winners of the 2021 Shaw Prize in Astronomy for their work on magnetars. It's the first time two women have been awarded the prize in a single category.
Krista Kuvelyato liked the night sky growing up in Greece. She knew she wanted to find out more, and getting a special gift from her father helped turn her towards a career in astronomy.
I just looked at the stars and I just figured something is hiding up there and we have to figure out what it is and maybe even go there. And basically that's what started me. And I should say I owe a lot to my father as well, because when I was a kid, let's say 10 years old or something, grammar school, basically he gave me a very beautiful cosmology book. In these days, cosmology was not as developed as we know today, but they had beautiful pictures, and they had also very nice pictures of the planets in our solar system. And I was taken completely from this book. So I kept reading it and didn't understand a lot, but it was actually beautiful. So that's the first interaction I had with astronomy.
Along the way, a high school teacher convinced her that physics would be an excellent career choice, even for a woman, which at the time wasn't what women studied. But become a physicist she did, and then an astrophysicist, after studying in Athens, Britain, and Germany. Her path led her here, George Washington University. The 43-acre campus sits in the heart of Washington, D.C. And it's where Krista Kuvelyato studies some of the most extreme objects that nature can produce in the universe. A neutron star is the remnant of a massive sun that has reached the end of its life, literally going out with a bang. What's left is a neutron star, a much smaller, much denser celestial carcass.
Neutron stars come in different varieties. Magnetars is one of the most extreme of them. They have properties that are not accessible on Earth. They have extreme densities, extreme gravity, and extreme magnetic fields.
Krista and her team confirmed the existence of magnetars in 1998, which had only been predicted in theory. But there were clues of their existence, repeating and persistent bursts of energy from a particular location in the night sky.
When we were looking at these repeating bursts, maybe we are actually discovering a new phenomenon. But all we had were the bursts. We knew the general direction in the sky of where this was coming, and therefore we could sometimes get the bursts, but we had to actually point a satellite towards that direction and get more information, like the persistent emission.
She wrote a proposal asking to use the Rossi X-ray Timing Explorer, a satellite that proved predictions in Einstein's theory of relativity, among many other valuable observations. It was approved, and with the data gathered, they were able to measure the spin of these objects, and with that, their magnetic fields. Very powerful magnetic fields.
It was 8 times 10 to the 14, 6 times 10 to the 14 for the other source. We looked at two sources. So the first paper was published about the existence of magnetars in 1998, if I remember correctly, and I was the first author because my team and I discovered that. And that was the first time that we actually had solid measurements, or I could say measurements of this magnetic field strength. So that started the magnetar family.
A lot of people, if you think about what are the most extreme objects out there, people often say like, oh, black holes, because they're so mysterious. But also magnetars, they're so extreme, they're extremely massive, but also extremely compact. And then they have these magnetic fields that you cannot really even dream of recreating here on Earth or in any kind of lab. And by just studying them, by observing them, we actually get to study physics under these very extreme conditions.
The magnetic field around Earth, the thing that protects us from the charged particles of the solar wind, is about 1,000 trillion times weaker than a field produced by the magnetar Chrissa found. Barely a fraction of a fraction.
What is the strength of this dipole field? And it turns out to be basically the largest that we've ever measured in the universe, and still to date.
We can understand better the theories and the models that have been developed here on Earth by observing properties of sources that have extreme values, and we cannot produce them here on Earth. In other words, we use them as probes of the extremes. And we're trying to understand how physics work in the extreme environments and how different they are from what we call normal here.
Chrissa first started looking for magnetars while she was working at NASA in Huntsville, Alabama. A job, she says, was always a dream of hers since her school days. She clarifies the popular notion that NASA just blasts rockets and astronauts into space, ignoring the fact that the agency does science too, lots of big science, such as in her field of high-energy astrophysics.
NASA has scientists, about 30% in the science centers, which is JPL and Goddard. Basically, and actually even other centers all of NASA centers have scientists, and all of NASA centers have a specialization in a particular direction.
Colleagues say she likes to build strong relationships with her co-researchers.
She built a family around research. All her colleagues are part of a family. Actually, all the young scientists part of the group here have been mentored and trained by her from the very beginning. So she has already been extremely careful of people. She knows the skills of all the researchers around her. She knows how to build a team. When there is a specific project, she knows where to get the skills, who she has to work with.
He says one of the advantages of working at NASA is that scientists get to use all the latest tech, which wasn't always the case, especially when Chrissa first started.
Chrissa has been working there at the beginning of her career. And I heard many stories about her going across the campus at Goddard, carrying tapes with data on them to analyze those data. So what were the technology 15, 20 years ago?
She and her team eventually used digital and network technology to analyze data. Chrissa spent 25 years in Huntsville before retiring in 2015. She joined the physics department at George Washington University. Chrissa is currently the chair of the department. Colleagues say she had definite research advantages being on the NASA team.
You're more directly involved in the development of new missions, new instrumentations, and so, which of course, can happen at the university as well, but there's a more direct link to the people actually building the missions, developing the missions, and then you as a scientist have a bigger chance of actually getting direct access to the data earlier because you're part of a mission team, for instance. So it's a little bit different than as a scientist, but as a scientist at a university.
At NASA, I did not have to teach, I did not have to prepare classes, I did not have to do anything else but research. So that was much more effective, much more productive.
NASA was also where Chrissa met her husband, Jan van Paradijs, one of the world's leading astrophysicists. He and Chrissa collaborated on many studies, co-writing 89 papers together. Passed away in 1999. During their working life together, they shared many ideas about their work.
Way too many And that's why I recommend that you don't marry exactly the same person in your work environment, because you can't get away from work. I mean, you come back home and you talk business again instead of talking everything else. But it was extremely useful in that sense, because we had students together. We were working on a lot of things together. We were very successful as a couple. And he was my soulmate. I mean, unfortunately, cancer took him.
Chrissa shares the 2021 Shaw Prize in Astronomy with Victoria Caspi, the first time two women have won a Shaw Prize in a single category.
Hey, great. I mean, we love it. There's no way I would have expected it. It happened. I think it was about time to happen. The conditions were right. I'm just grateful to the committee for the nomination. But I am very exuberant with the fact that two women got the prize.
We'll meet co-winner Victoria Caspi after the break. Victoria Caspi has made a career looking for spherical objects, ones that you can't hold in your hands or pass to the kids on the basketball court.
I'm on.
The spheres she's after are a type of neutron star called magnetars, objects that lie millions of light years away from Earth. They're some of the most extreme objects in the sky. Observing unusual X-ray emitting pulsars, Caspi confirmed they were actually another type of magnetar, establishing them as a distinct new group of objects. It was a slam dunk.
Finally.
They exhibit really unusual and dramatic, violent phenomenon like large X-ray bursts, soft gamma ray bursts, and now we even know they also emit huge radio bursts as well. And we know of a couple dozen of these in our galaxy, so they're quite rare objects. But we think they're basically an extreme member of the neutron star population.
She had just entered the field of astrophysics when there were new X-ray satellites being launched. They offered the chance to get in on a promising field, literally from the ground up. She was inspired to look at unusual X-ray sources after a lecture she attended at the California Institute of Technology.
They had all these weird X-ray properties and were a total mystery. People did not understand what they were, and that caught my attention. And from that lecture, I had some ideas about how to attack the problem, and that's what they turned out to be magnetars. And it was from hearing this lecture from outside my field and having known a little bit of X-ray astronomy, I realized, I can apply some of what I learned in my PhD, bring it from radio astronomy to X-ray astronomy, and I thought I'd give it a try, and I did, and it worked.
The significance of Vicky's work is that she solved a big mystery in astronomy, namely these objects known as magnetars. So for a while, people were making observations and just had no idea what these things were. And now we know that these are essentially neutron stars that are some of the most extreme objects that we know of. And basically, Vicky came along and figured out what these extreme objects were.
Growing up in Texas, Caspi loved to solve puzzles when she was little and found that math was her favorite subject. And she was good at it. She set her sights on a career in some form of science.
At the same time, I was a huge Star Trek fan, and I really enjoyed thinking about the cosmos. I liked reading Isaac Asimov books about science fiction, things like that. And then really, I would have enjoyed doing almost any kind of of hard science, hard quantitative science. But I had the opportunity to do astronomy. I got a taste of it and I fell in love.
Caspi has admired the work of women in science, including her co-winner, Krissa Kovelyato. But her admiration goes farther back.
I was very inspired by Marie Curie. I thought her life was fascinating. I thought she was an amazing person, tenacious and brilliant and hardworking and so accomplished. She was definitely a role model for me as a kid. Then I would say in university, my role models, you know, my PhD supervisors were wonderful role models, Joe Taylor and Dick Manchester. They were also very thoughtful scientists, very meticulous.
Caspi continues her pursuit of high-energy astrophysical phenomena as the director of the McGill Space Institute at McGill University in Montreal, Canada. Now she is the mentor, advising the astronomers of tomorrow.
She cares a lot for her graduate students, and she cares a lot for the work that she does. And she wants her graduate students to be excited about what they do, and she wants everyone to be doing what they love and feeling just as passionate about their work as she feels about her work.
She hopes to pass on the things she learned from her own teachers. Be meticulous, systematic, trust your instincts, and if something goes wrong, stay cool.
My PhD supervisor in Princeton University, he was a very friendly person. He taught me skills of interacting with others. He was just a master at doing that, very inspiring in that way. And of course, he taught me a lot of science as well, about how to use, how to analyze pulsar timing data, different style of pulsar timing data. But overall, I think what I took away from them is love of science and you know, enthusiasm and how to share that enthusiasm with others.
One of her former students thinks Caspi brings a great curiosity to astronomy, keeping her on the lookout for new stuff to discover.
One thing that I think makes her very special is that she always tries to push herself towards brand new science and astronomy work that comes out So it's like she won't get stuck working on the same thing over and over, but she'll like pursue new frontiers in science, and that's like what I think it's like very unique to her.
Caspi's fresh new puzzle that she's trying to solve is the mystery of fast radio bursts, or FRBs, a radio pulse from an unknown source lasting milliseconds, first observed in 2007. The race to identify these phenomena has turned into a mad scramble to observe more of these mysterious events, which occur outside the boundary of our own galaxy, the Milky Way.
I think that fast radio bursts is one of the hottest topics in astronomy currently. I mean, you've got people all over North America, you've got people in Australia, you've got people in Europe, you've got people on every single continent working on these objects.
The commissioning of a telescope in British Columbia, Canada, revolutionized the field. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is a collaborative project where Vicky is the principal investigator. Normally, radio astronomy can focus on one point in the night sky, but CHIME can reel in vast swathes of data, more data than in all the world's mobile telephone networks, 13 terabytes per second.
We populate the axis of the cylinders with hundreds of antennas, and then in a computer, in a supercomputer, we combine them and we can be sensitive to different positions on the sky all at the same time. So it's like having, in fact, we have 1,000 of these. It's like having 1,000 telescopes all operating at the same time, 24/7.
The number of bursts measured by the facility over time was exponential in scale. The new telescope detected over 2,000 fast radio bursts in just a few years from its launch in 2017. The field had exploded.
We're detecting lots of these things, and we see like these interesting structures. We call this the sad trombone effect. you see it starts, it's earliest at high frequency and then comes down. And that's not dispersion because we've corrected for dispersion here. This is something at the source, and we call it a sad trombone because it goes like wah, 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 like that. And we actually make that noise in public talks because it's so funny.
Like magnetars, FRBs could reveal much of what we do not know yet about the universe.
Maybe we can use fast radio bursts to detect dark matter. Or maybe we can use fast radio bursts to study the early universe. Or maybe we can use fast radio bursts to learn about these faraway galaxies that we don't already have a lot of information on. Or maybe we can learn a bit about our own galaxy using these fast radio bursts. Or maybe we can learn about the stuff that lies in between our galaxy and other galaxies. And so there's really this wide range of study for these objects.
Victoria Caspi shares the 2021 Shaw Prize in Astronomy with Krissa Koveliato. The first time two women have won the Shaw Prize in a single category.
I'm deeply honored. I'm delighted to have been given it with Krissa, who is a formidable, brilliant scientist. I think there are many, many extremely capable and accomplished women who I feel confident will be getting Shaw Prizes going forward. So we might be the first, but I'm 100% sure we won't be the last.
Good evening and welcome to our special on the 2021 Shaw Prize. For the Life Science and Medicine Award, American molecular biologist Scott Emmer discovered the escort pathway. This mechanism is a key aspect of membrane biology, central to important processes, including cell division and viral infection. The understanding of this mechanism enables scientists to look deeper into health issues such as cancer, Parkinson's disease, and HIV.
The workaholic who never stops, not even in his sleep.
You tend to be thinking about it at all times of the day and even the night. In fact, I used to keep a pad next to the bed on the table, and I'd often wake up in the middle of the night with an idea that for an experiment, but a few of those ideas turned out to be very productive.
The teacher who inspired many.
The discovery was in the field of multivesicular body biogenesis, but his vision and the approaches that he took transformed that discovery into what is now a very general sort of phenomena in biology.
What I like the most about Scott is how excited he becomes when he figures out an idea, and that excitement is infectious because you're sitting with him and suddenly you'll see Scott's got this idea and he's super excited about it, and suddenly everything feels more exciting about that idea.
Scott Emmer, director of the Weil Institute for Cell and Molecular Biology at Cornell University. The 67-year-old unpacked the secrets of a mechanism that cells use to bend membranes in a unique manner. The mechanism is central to vital biological processes, including cell division and budding viruses. His landmark discovery of the endosomal sorting complex required for transport pathway, or escort pathway, provided new perspectives to research into health problems that trouble billions of people worldwide.
We never anticipated that we would uncover genes that were so specific for this unique pathway within the cell. As a basic scientist, we were most interested in just the fundamental question of how does the system work? How does the cell build this organelle? Because we use genetics, we ask the question to the organism. And by getting the mutants, the organism feeds back information by revealing the genes and the proteins that guide these processes. It was just through our simple hypotheses and then designing genetic tools and experiments that will allow us to find these mutants.
To Scott, it has always been pure joy to dig into these biological mechanisms, and his love of science dates back to childhood.
My father was manager of a factory in New York City, and my mother was a housekeeper. I had two brothers and a sister, but they encouraged whatever we were interested in. As a small child, I always enjoyed being outside and just observing things, especially the stars and planets and so forth. And we had a set of encyclopedias in our home, and I would scan through those as to, what's going on in the world, how, biology and physics and so forth. And I sort of leaned towards biology.
But science is a very wide subject, and it took some time for the molecular biologist to emerge from the student. Marine biology was one of the possibilities Scott considered in university, but he soon found out it was not for him.
In my sophomore year, we got to go out on a research vessel in the Atlantic Ocean, and it was fairly boring. It was nothing like the Jacques Cousteau shows that they showed on TV.
He decided to switch to a career that allowed him to see how the most basic biological mechanisms work: molecular genetics.
It just opened my eyes to what bacterial genetics was capable of doing, that you could, on simply using agar dishes, find mutants that exhibited defects in individual pathways. And then by characterizing those mutants, you could identify the proteins and genes that function in those pathways, and ultimately figure out the enzymatic mechanisms.
How proteins get in and out of a cell is a problem that has captivated him all through his career. This process, known as membrane trafficking, involves specific compartments within the cell. Scott's work focused on how these compartments are built. Looking into the organelle responsible for degrading and recycling of cellular waste eventually led to his landmark discovery of the escort pathway.
We wanted to understand how the cell builds this organelle called the lysosome. How do you bring the membrane and the proteins to this organelle? And so we used yeast, a simple unicellular eukaryote, where you can apply powerful genetic tools to look for mutants that had defects in the assembly of the organelle, the lysosome. And among those mutants were mutants that ultimately fell into the escort group of genes. And by characterizing the genes and their products, we slowly were able to develop hypotheses as to how the escort system might work.
Lysosome can be understood as the recycling center of the cell. Cellular waste, or damaged membrane proteins, is sorted away from the functional ones and delivered to the lysosome for degradation. Endosome is the central sorting station, one stop along the route to the lysosome. Scott explains that at the endosome, the escort machinery selectively sorts membrane proteins and encapsulates them by bending inward the endosomal membrane. The vesicles are then delivered to the lysosome, as the endosome becomes a multi-vesicular body and fuses with the lysosome. The mechanism is unique, as vesicles bud away from the cell cytoplasm, the opposite direction they normally bud in other subcellular organelles. Regulation of signaling by cell receptors and cell divisions are among some vital processes that involve the escort pathway. Since publication in 2001, there have been widespread applications of the escort pathway in cancer and neurodegenerative disease-related research, and HIV infection, in which the virus uses the escort pathway to bud and spread to new cells. Asked what enabled his achievement, Scott thanked his mentors for their great lessons and support. One of them is Randy Schekman, winner of the 2013 Nobel Prize in Physiology or Medicine.
They each, in many ways, saw things in me that I didn't see in myself. My mentors, both at Harvard, Tom Silhavy and Jonathan Beckwith, as well as at Berkeley, Randy Schekman and Jeremy Thorner, seeing how Randy oversaw the lab and offered suggestions in a way that allowed the student and the postdocs to come up with their own ideas and then pursue them. So he gave us a good deal of freedom in how we thought about our problems and developed them, but he also offered very important insights that helped to guide me as well as others in the lab into our careers.
And the most important person, Michelle, his wife of 44 years.
When there's difficult times at the lab or experiments aren't going well, when I walk in the door in the evening and come home, my wife can usually read my face immediately and be able to determine if it was a good day or a bad day of science for me. And she is very supportive all the time and has always been the strongest person and friend in my life, and I thank her very much. She's my angel.
But was it easy to keep the family together with 2 children and a spouse so devoted to his work?
Yes, it takes patience to be a scientist's wife, and at times it can be lonely when he has to stay late or if he has to travel to conferences. Taking care of kids on my own was difficult.
How did you do it?
With patience. Well, we complement each other, and opposites seem to attract. He loves his science, and I love my teaching, gardening, and talking with my grandkids on FaceTime and reading them stories for an hour or so. But what gives me more joy is being with Scott on the weekends, traveling together. And we love each other dearly.
Till this day, Scott and his lab are still trying to learn more about the escort complexes or the division of labor between them. He advises future scientists to look where no one else is looking to find subjects to study.
Continue to do what excites you, and as you develop your research problem, look for problems that are not the hottest thing on the market right now, but try and define a problem that you can make your own and not be competing with others.
Welcome back to our special on the 2021 Shaw Prize. The co-winners of the prize in mathematical sciences are Jeff Cheeger and Jean-Michel Bismuth. They share the award for their work in modern geometry that has transformed what is one of the oldest branches of mathematics.
Mathematician Jeff Cheeger likes a walk in the woods to think about geometric problems he wants to solve. But in the U.S. state of Maine, a paddle on the water will do, helping him to analyze the spaces of mathematics.
The thing is, Jeff is in the interface between space and calculus, right? He uses calculus very powerfully, thank you, very powerfully in his analysis of space.
Colleagues say Jeff Cheeger has done foundational work connecting several different areas of mathematics, from differential equations to differential geometry and topology, among others, which has served to integrate different perspectives on geometry. And he does it to create understanding in his own way.
Jeff is, one of his strong points is thoroughly analyzing and trying to understand not only what you appear in the surface, but what's behind it. And this is part of what it means to be a good mathematician, to see what's behind things. And then if you're very thorough and put a lot of work into it, you can make progress.
Growing up in Brooklyn, New York, Jeff got an early start on his exploration of mathematics thanks to his father.
My father introduced me to math when I was about 7, so he taught me some elementary algebra, and I really liked it. I liked the idea that I knew something that the other kids didn't know. I seemed to be good at it. He would teach me more intermittently, but not systematically, not in any way like he was pushing me.
He wavered about studying math or studying physics for a while and was 90% certain that math was the field for him. But he hadn't entirely ruled out physics, that is, until his first year at Harvard.
After the first year in college, I ruled it out. It was clear. And I had a very exciting math course that I took as a freshman with a very inspiring teacher, Shlomo Sternberg, and that also played a big role.
He went on to get his PhD in mathematics at Princeton. He says the final appeal of math was the certainty of its findings. It's been the same since the time of Pythagoras and Euclid.
Math uniquely builds on itself, right? Because once something is proved, then it's always going to be true. So it can build on itself over millennia, and people in different cultures and different races, and none of that makes the slightest difference because the theorem doesn't care about who proved it. So in my view, math is a high-level unifying force for mankind.
Jeff likes to show guests mementos collected over a long career in mathematics.
Here was this is a very close friend and colleague, a real genius, Misha Gromov. So this was for our 60th birthdays. And here I had, at this time, 5 Chinese students from mainland China. See all these guys? This here, they made for me. It's a tradition in China. When you get your PhD, you go to your advisor's house, and this says something like, great teacher, useful friend, or something along those lines. So this is very traditional.
While Jeff studies his geometric spaces, Shirley Chigger fills her space with pottery. Shirley says she will never understand his work, but admires him for his thorough approach.
So he spends a lot of time working. He's very serious about it. Because he is who he is, he thinks about just about every question very thoroughly. So sometimes it doesn't really need a detailed answer. It just needs a yes or no answer. And other times, the way he thinks is enlightening, inspiring.
The Chiggers' wedding came after a chance meeting at a high school reunion.
We met at our 30th high school reunion. So we went to the same high school, but it was a very big high school, so we didn't really know each other. There were about 2,000 people in our graduating class. But 30 years later, we met at our first reunion. Is it clear, or is the math too complicated?
We were in our 40s at the time.
If that helps.
In New York City, Jeff Chigger is the Silver Professor at the Courant Institute of Mathematical Sciences at New York University, in the middle of Manhattan. He joined the faculty in 1993 after stints at Princeton, the University of Michigan, and Stony Brook University. Colleagues here say Jeff's work is characterized by great originality and courage in terms of the problems he tackles, which are known to be very difficult.
So it takes both great ability and great determination to work on problems like that, and he's demonstrated all of that repeatedly in different directions, in geometry and in high-dimensional geometry, and it in turn has repercussions in other areas of mathematics.
Although Jeff is a theoretical mathematician, Kappel says his work will help advance research in the physical world, in applied science, and engineering.
Some of the methods that Jeff pioneered in continuous geometry in geometry of shape and form have in turn had applications by being extended to discrete geometry, to things like the web and searching on the web. So indirectly, his ideas have influenced things like web search as well. So they're important in ways that could have been anticipated, and also in novel ways that could not have been anticipated. They've had an influence in that kind of broad range of subjects.
A Cheeger solution that will have an impact for years among many others is the Cheeger constant, a major breakthrough and described as the smallest area of hypersurface that divides a manifold into two parts.
The Cheeger constant, for example, this methodology has been used in many places, in theoretical computer science and graph theory, various places in discrete math, and so on. So I'm sure that those applications have downstream impacts on design of devices and algorithms and so on.
On winning the Shaw Prize, Jeff Cheeger takes a modest view of his achievement.
Certainly it doesn't require genius, although there are mathematical geniuses. So I like to think of it this way. You could think of it by analogy with a sport. So a key point is there are many levels and many ways to make a meaningful contribution.
Paris, the city of lights, but also a city of mathematics. Jean-Michel Bismuth takes a stroll with his wife. In a career that spans more than 50 years, he has solved long-standing open problems. He built tools that have greatly extended the range of what is possible in geometry. It all started when he found he had an aptitude for science as a teenager. The field he initially liked the most was physics.
And everything which was done at the time in modern physics, I was very enthusiastic about this. But in some sense, I decided to do math instead, because to be a physicist, you need to have a sort of drive to understand reality as it is, and I'm more understanding reality as I make it. I mean, as I build it for myself.
Jean-Michel graduated from the École Polytechnique and earned his PhD from the University of Paris. Was it here he began to see he could build his own mathematical facts?
In physics or in other fields like biology or medicine, you need to interest yourself to things which are dictated to you by the facts. When you're a mathematician, you can decide in some sense where the facts are. You can create the facts for yourself. At least you can invent things, connections between various fields, which you decide, you construct them.
Bismuth is currently an emeritus professor at the Department of Mathematics of the University of Paris-Saclay. Colleagues say Jean-Michel has demonstrated great versatility and courage in his work.
What he did essentially was to apply probabilistic technique, which he mastered very, very well, to geometric problems, and very difficult geometric problems, which need a kind of a tour de force in terms of calculation.
It's the depth of what he is doing. So far as I know, probably since he was young, he has never attacked a problem which was easy. He has worked on problems which are extremely deep, and he has himself introduced techniques which now apparently in his field are just normal, even routine, but which he was really the first to use.
Bismuth continues to work on difficult problems, where these days he's looking at questions related to basic structures of truth and mathematical truth.
My kind of mathematics is not applied. There is definitely not, I could not say, even though, it leads to concrete computations, but the computations, the results, are not directly intelligible by anybody willing to apply these to concrete day-to-day problems. Certainly not.
Jean-Michel Bismuth shares the Shaw Prize in Mathematical Sciences with co-winner Jeff Cheeger for their transformative work in geometry.